Can you tell the difference between a quadratic and a linear function? There's my intro. We're going to get a little bit better at this by the time this is done. I'm going to jam through this. This is going to be quite a bit. Hopefully this will be less than a 10-minute video. Jumpstart. When I look at a table, I recognize it's a linear function if it has a constant first difference. When I look at a graph, I recognize a linear function if it's a straight line. When I look at an equation, I recognize it's a linear function if it's in y equals mx plus b, or f of x equals my beginning value plus my rate of change, ROC, times x minus 1. If it's in that form as well, there I know it's linear. All right, moving on. Marco has started a blog about sports, okay, at Imagination High School. They are the Fighting Unicorns. Yay, Fighting Unicorns. He started a website called Eyesight, and he created a logo that makes it look like the one below. Okay, it says above, but it's below. He is working on creating the logo as various sizes to be placed in different pages on the website. Here's the following designs. So, size 1, size 2, size 3, size 4. How many squares would be needed to create a size 100 logo? Well, the first thing you have to do is study what is going on here. There's multiple ways you can look at this, all right? So what do you notice about each of these blocks? Well, gee, I notice size 1 has 7. Size 2, I'm going to say 2, 4, 5, 10, 12. 1, 2, 3, 4, 5, 6, 7. That'd be 14, 18, 19, 20. This is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 18, 19, 20, 21, 22. How's it growing? Okay, so we can use a table. Essentially, that's kind of sort of what I did. And I'm going to jump ahead here a little bit, if it'll let me, because it wants me to fill out a table and a graph anyway. So since I'm going to fill out a table and a graph anyway, 1, 2, 3, and 4. Size 1 had 7. Size 2. What was size 2? And we got to go back. 12, 20, and 22. So 12, 20, and 22. All right. Now it's telling me there's only a first difference. So if there is only a first difference, 7 to 12 is plus 5. 12 to 20, what is that? Should also be plus 5, right? And then 20 to 22, that's not right. Something's not jiving here. One is not jiving. 12, 20, and 19. Should be 20. No, that's right, 12. 1, 2, 3, 4, 5, 6, 7, 14, 15, 16, 17. Aha, 17. How did I not count that right? And 17 to 22. So there should be our plus 5. Okay, so this should be 17. And then plus 5. 17 to 22 is plus 5. So if you see what's happening here, plus 5, we can fill in the rest. Figure 5 or figure 6, right? We're going to have 27, and we're going to have 32 is what we should end up having, right? But what is actually happening with our diagrams? Is there a quicker way to count this? Because it says how many squares are going to need to be in the size 100 logo. I'm not counting all the way here. I notice that this is 3, this is 5, this is 7, this is 9. I'm not going to sit there and continue to count that way. So how else can I see what's going on? Some people may recognize, okay, that was one thing that you may recognize. Some other people may recognize that, hey, the center section in the first figure is 1, in the second figure it's 2, in the third figure it's 3, and in the third figure it's 4. Very good. You may also recognize that this upper part up here is 1, second figure is 2, third figure it's 3, fourth figure it's 4. And likewise, I'm going to have 5 groups that do the same thing. Well, guess what? If the first figure in this corner has 1, the second figure has 2, the third figure has 3, the fourth figure has 4, by the time I get to the 100th logo, how many is going to be in here? There should be 100. All right? So 100 times 5 groups plus 2 extra, because each one we have 2 extra, is going to be equal to 502 blocks. All right? That's one way to look at that. Now that's tough to see. Yes, I agree. Now it says develop a mathematical model for the number of squares in size logo n. Well, first of all, we know based on the table, it's a constant rate of change of 5. So if it's a constant rate of change of 5, f of x should be equal to my beginning value, which is 7, plus my constant rate of change, 5, times x minus 1. Okay, look at it straight out of the book. Okay, now we need to fill out the table. All right, I'm not gonna fill out the table and plot the points for you just for sake of time. I want you to do that. But down here should be figure number 1, 2, 3, 4, and so on. And over here should be the number of blocks. All right, and I would probably increase this by 5s or 10s. So 10, 20, and so on, and you continue to do that. Make sure you get that filled out. Pause and get that done, and I will just give you a clue. When you get done with your graph, it should be a straight line. All right? Moving on. Marco decides he wants to make it look a bit blockier, so he toys with the design. So what's going on here? Well, let's keep in mind how we broke up the other figure. We broke up the other figure by looking at a section of the eye. That is how we did that. Assuming that Marco continues with the pattern as it began, draw the next figure in the sequence. So pause a second and see if you can draw the next figure in the sequence. Noticing 1, 2 by 2, 3 by 3, so what should be here? So pause and draw it. And if you've come back and you've noticed that this should be 4 by 4, you're absolutely right. So I should have 4 by 4, 4 by 4, 4 by 4. And that should just continue. The center section should be 4 by 4. Over here should be 4 by 4. And down over here should also be 4 by 4. Right? And I'm going to have, I can kind of look at all of these that way. All right? There's a 2 by 2, 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 there's a 2 by 2. So I should have 7 groups of 1 by 1, 2 by 2, 3 by 3, or 4 by 4. Assuming Marco continues with the pattern he's begun, the next figure and how many blocks? 4 by 4, because that's the one block we looked at, right? This area right here, that would be 4 by 4, times, how many groups did we have? We had 7 groups. Well, that's going to be 16 times 7 for a grand total of 112 blocks. All right, I hope you're following along. Now we're going to take that data. We still have figure 1, 2, 3, and 4, but now we need to total all that up. Well, figure number 1 still has 7 squares. Figure number 2, now remember, I had 5 groups, or excuse me, I had 7 groups. That first group was 2 by 2, which is 4. 4 times 7 is 28. I don't want to count 28 boxes individually by ones. I don't want to do that. So I'm going to use some grouping and some multiplication to help me out. 3 by 3, 9. 9 times 7 is 63. 4 by 4 is 16. 16 by 7 is 112. We already did that. All right, so we should see that there. And then if we go ahead and we do a first difference, we have plus 21. Plus 35, and plus 49. Our second difference is going to be plus 14, plus 14, plus 14, plus 14. That's what's going to happen. And if we go ahead and fill the rest of this out, which I'll just do 5, okay, that's a 14 difference, so we would get 63. All right, and then we end up with 175. Because 112 plus 63 is 175. And again, pause and go ahead and fill out the table. We're going to have size number 1, 2, 3, 4, 5, and 6. And you're going to have block numbers here again. All right, so make sure you number that accordingly. And then it says develop a mathematical model. We pretty much already did. If we come back in here, 4 by 4. What if it was 3 by 3? Could I do 3 by 3 times 7? and get 63? Could I do 2 by 2 times 7 and get 28? Could I do 1 by 1 times 7 and get 7? So here's our mathematical model. Any size n, any size I go to, the number, the height, times the width of that one section times 7 sections is going to give me 7n squared, if I kind of clean that up, right? Compare the models we developed for the first set of logos to the second. There's some similarities and some differences, right? There's a lot more differences than there are similarities. One of the sims is that f of 1 was equal to 7. The first term was 7, that was a similarity. Differences in the equations. The equations were squaring 1. Okay. The difference from a table is first and second differences. And from a graph, we have a straight line versus curved line. These are kind of the key differences in linear and quadratics, and especially when we look at these two examples. Now, for this, I am going to jam through this again because this is going long, but you need to understand linear versus quadratic. The rate of change of a linear function is constant. In a quadratic function, it's linear. The diagram, how do the diagrams grow? The diagram grows in one dimension. In a quadratic function, two-dimensional growth. An equation, here's the biggest distinction between the equation. Y equals x or y equals x squared. The square being the big one. We have seen our linear functions like this, where we have a begin term, and then we're going to add our rate of change, our ROC, and then the x minus 1. That's how we saw another linear equation. The table only has a first difference. Here we have a second difference. The graph is a straight line. Here it's a parabola. Right? And then your lesson summary. Summarize what you put in there. Your sentence. All right, there you go. There's it in a nutshell. Ask questions, please.